Feel free to ask me any questions if you have them. We've got about 6 minutes. I just logged in case anybody had any questions for now. I did just send you guys an email. Hopefully you saw that too. All right. Hey, Miguel. Hopefully you saw your email. I just sent one out to the class. So check that out. You're welcome to ask me questions. We still got about 4 minutes before the class starts, but I just want to make sure you saw the email. Oh yeah, go ahead and chat me your first and last name, so I'll have that as your role for today. Hmm.
So,
Yes.
Um, uh, what I talked to you about in the last class, the practice test, it's still not resolved.
Yeah, I'm working on some stuff regarding that. Was that Jennifer that asked me that, or was that
Yes, that's me.
okay? So did you just get the email I just sent you?
No,
Okay, I just sent an email regarding both the exam that was supposed to happen this week, and in case someone did take it this week, what to do. So basically, I've moved the test that we had that was face to face. I'm now making it due by Sunday of next week, and people that actually took the test, there's a couple. If they actually took the test, they can keep the score they got, or they can take it again, and I'll give them the higher of the two.
I'll probably take it again.
Yeah, I'm having some technical difficulties with some of the tests, the online tests and practice tests. So I should have that remedied by tonight. And I put in the email that we could do the test any day next week. It's just a matter of you'd have to find another testing center, or you could come up. I could proctor it for you as well, but you'd have to go somewhere. But
They had said that I couldn't keep my scratch work.
yeah, I got
So
it.
that's why I had them email it to you, because that is how I fix what what I'm missing in, learning or whatever.
Gotcha. Yeah, no
Yeah.
problem. I did get that. So and actually if you need it, I wouldn't mind giving it back to you. It's not a problem.
Okay, I wasn't sure if I was allowed to have it.
Yeah,
She
not
said she
only
was
that,
gonna throw it away, and I was like, oh, no, 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 because that's very important.
yeah, not only
My
that, we're supposed
precious.
to I'm trying to set it up when you take those online tests where you can go back and look at them at any time later. So if you're unable to click in the grade book on your score for that test and then see the test, let me know because I got to figure out some way to make sure everybody can see that because I want you to be able to look at that. I want you to be able to resolve those problems and figure out what the right answers
Yes.
are. Okay.
Yeah.
I'm able to.
Okay, great. Thank you.
You're welcome. Anybody else have any questions? I did ask everyone to go ahead and chat me your first and last name. Corey, you didn't do that, but you did send me a message, so that's a little better. But at least do everybody send me a chat with your first and last name. We'll have that as our role. We last time solved some pretty tough. Oh no, that actually I was thinking something else. Sorry about that. Last time we had done some physics problems. I actually worked out the scenario of centripetal acceleration and stuff like that. So I have some more problems that I want to work along those lines, and that's what we're going to do today. But before we get started, does anybody else have any questions? I'm trying to look back at what just to make sure I remembered exactly what we did last time.
I did have a question. It was one of the questions I had on the test, and it wasn't anything I ran into in the practice tests. It was
Okay.
it was a mass on an incline, and it just gave like I think the acceleration and asked you to find the angle of the incline.
Gotcha.
I had no idea how to do
Did
that.
it have friction?
No, it gave you acceleration, and I can't remember if it gave you mass, but it only gave you like one or two pieces of information.
I think I remember that problem. What you're supposed to do is just do g sine theta. So the acceleration is supposed to be equal to g sine theta, and then you just solve for, in that case, theta. Do you
Okay.
recall where that came from? Where the g sine theta, how we managed to get that?
It's because you have to break up the forces underneath, right?
Exactly. The mg that comes straight down, we have one that's perpendicular, that's mg cosine theta, and then we have one that's parallel to the plane, that's mg sine theta. If that's the only force acting on the object in the x direction, then you've got mg sine theta is equal to m times a. The m's cancel out, and that just leaves with a equals g sine theta,
Oh, okay.
which I think also I referenced that as like it was like one of the first or second, maybe even third episode of Big Bang Theory. So, where they had to carry something up the steps and they estimated that the steps were 30 degrees and G sine theta and all that sort of stuff. So anyways, I just made that reference. I knew I covered it, but if you have any problems with it, just let me know. But that should be the answer. That question may or may not appear on the test, the next version. It looked like neither one of the people that actually took the test, it didn't look like anybody had any problems with the time allotted. Did you feel rushed, for instance, Dylan, or
I
anybody else is willing to answer?
They didn't tell me how long I had, but I did it until close, and they told me I had to hurry up because they were about to close.
Okay, gotcha. So you probably did take the full hour and 20 minutes or something like that.
Oh, if it was only an hour and 20 minutes, I think I took longer than that because I started
I
at
also,
four.
go ahead.
Go ahead,
Sorry.
Jennifer. I think you finished.
I was gonna say, I took way longer than that. And I need extra time.
Okay,
So
gotcha.
thank you.
If anybody, by the way, and not to say that's about her or anything, but if anybody does have an accommodation, make sure you let me know. I normally get emails from someone, but I don't recall getting any emails from anyone this semester. But it could have just been that I missed them. So if anybody has an accommodation, make sure you send it to me or get your person to send it again. I will look again just to make sure. But yeah, I do. I have to honor those. So if anybody has any kind of accommodation, extra time for the test, that sort of thing, I don't mind doing that. I will do that. That also can sometimes cause some problems with the testing center. For instance, their standing rule, at least as far as I've known, is like, let's imagine they're closing at 5 p.m. If they're closing at 5 p.m. and I've got a test that I've said you're allowed to have an hour and a half for, then you have to start no later than 4 because they want an extra 30 minutes in case anything goes wrong. So if you start at 4, the hour and 30-minute long test would be, or excuse me, before 34. If you started at 3:30, for instance, then the hour and 30-minute long test would be 3:30 to 4:30 plus 30 minutes would be 5. So that's as late as you could take it. So just remember that when I give you extra time, you might have to make a decision that I can't take the test during this time, or I have to take the test during this time and choose not to have as much time. So that's on you. I mean, you're completely allowed to not take it. That's fine, but just make sure you get that in advance. Anything else for anybody? All right. Well, what I'm going to do now is I wanted to work some more physics problems related to not necessarily friction because I've already done quite a bit with friction, but I haven't done hardly anything with centripetal acceleration. So I wanted to get you some problems like that. So let's begin with that. Sorry about the hemming and hawing. I was trying to do like 15 things at once, which means I basically did none of them very well. So anyways, I'm going to click on my Access Pearson because I found that the examples they have in the book are pretty darn good for these particular problems. So I'm going to pull them up and see if there's one specific or a couple specific ones that I want to do during this particular meeting. All right, so that's coming up now. I'm going to go ahead and share my screen. Whoop, that's the wrong window. I'm going to go ahead and share my screen with you folks. There's my iPad screen. Okay. So now you're looking at my iPad. I'm double checking into my chapter work on chapter 5. And specifically, let's see. Didn't see much there. Maybe it's here. Let's see what I got. I'm trying to look for a specific example of anything with friction. I think everything I did with friction was fine. Yeah, I'm happy with that. So remember last time what we were able to do by using that vector field, R vector equals R times cosine omega t I hat plus R times sine omega t j hat. we were able to take the derivative of that. And from the derivative of that, we were able to figure out what the velocity as a function of time was. And then we took the derivative of that and figured out what the acceleration as a function of time was. And then we were able to actually take the magnitude of each of those. So we could find the magnitude of the r hat, or excuse me, of the r vector. That turned out to be just plain r. So in other words, the thing was always a distance r from the origin, which is cool. Then we were able to take the magnitude of the velocity of a vector field, and that turned out to be a constant, v equals r omega. So that was pretty interesting. And then we were able to take the magnitude of the acceleration, and that also turned out to be a constant, and that constant was omega squared r. And then I plugged in v equals r omega, and that gave us v squared over r. So what I'm asking, the reason why I'm bringing this up is I want you guys to recall that we found AC is equal to omega squared r, but it's also equal to v squared over r. And that's the acceleration. It's the centripetal acceleration required to make an object go in a circle of constant velocity v. Okay. We also discovered that v is equal to r omega. And I made mention of the fact that omega was actually 2 pi over the period, where if you're going in a circle, the period is the time required to go from that spot all the way around back to that spot again. Making use of the fact that the period is in fact 1 over the frequency, we get 2 pi times f is also omega, so that can help us as well. The expression that I used to do that was f equals 1 over t, which you might notice also can be written as t equals 1 over f. This quantity is measured in hertz, or CPS, cycles per second, is what some older books say. Whereas this quantity is written in radians per second. And it's either called your angular velocity, or it's called your angular, or well, you could call it the rate of angle change or something like that. But normally we just call it omega, and we speak of it as the angular frequency or as the angular velocity. So we're going to make use of that stuff now. But the main thing is I wanted to make sure that you recall that was the formulas we got. So anybody have any questions on that? All right. So what I want to do is I want to estimate the tension necessary to keep an object in a circle. So example, what tension is required to maintain a circular orbit path or orbit if the object going in a circle has, I'm going to say the mass is equal to 0.150 kilograms. That would be 150 grams. I'm going ahead and jumping ahead and making that into kilograms. We're going to say the circle has a radius of 0.600 meters. And we're going to say the ball, the object, whoa, makes 2.00 revolutions per second. Okay, so that's what we're trying to figure out here. We're basically just imagining a object in a string being held by a string. We're rotating it over our head like this. And what we're going to do is try to figure out what tension in the cord must be to provide the necessary centripetal acceleration. So our solution is going to involve the summation of forces is equal to mass times acceleration. It's also going to involve and require the acceleration, which is omega squared r. We could also write that as v squared over r. That's acceptable as well. And we might also need to figure out what the actual velocity is. So I will tell you that velocity is equal to distance divided by time, at least the average velocity. But if you're talking a constant velocity, then the average velocity is the velocity. So that's acceptable. So we'll make use of all that stuff. We'll also make use of the fact that omega is equal to 2 pi over the period, and that's also equal to 2 pi times f. Okay. So what I'm going to do is I'm going to recognize that the 2 revolutions per second is actually the same thing as the frequency. Now, it's probably not that abnormal for you to look at it and say, I'm not sure that really is the frequency, because the frequency is supposed to be like in hertz or cycles per second. And this says revolutions per second and stuff like that. But here's the cool thing. What we know is the frequency is equal to 1 over the period, and the period is equal to 1 over the frequency. So if we can figure out what the period is, assuming this f is really the frequency, and we get exactly the right answer, that the 2 are reciprocals of one another, then we know that what we guessed is right. So I'm going to do that part as if I don't know, but I really know, of course. So what this says is 2 revolutions per second. So I'll put f is equal to 2.00 revolutions per second, which is also equal to 2.00 cycles per second, which I think is fine, right? And I'm sort of looking at this, trying to play the role of you, the new student to physics. So it's perfectly, reasonable for you to be somewhat doubtful of this, and I would hope you are somewhat skeptical of what I'm saying. So I'm going to show you how I actually work it out to make some sense of it. So if I'm going on the claim that the f is 2.00 cycles per second, then that would imply that the period t is actually equal to 1 over the frequency, which would be 1 over the 2.00 CPS. Okay. Well, guess what? That's exactly 0.500 seconds. So if the period is actually 0.500 seconds, then I know it's okay to consider that to be 2 revolutions per second. Your son's cracking me up back there. So, and it being the shaky blackout character, it makes it even funnier. Okay, so here's how I'm going to close the loop to make sure this actually works. So they told us 2 revolutions per second. So what that means to me is this thing's going 1 second right there. So it went 1 revolution, 2 revolutions in 1 second. So that would mean it completed 1 revolution in half as much time, because it did 1, 2 in 1 second. So it must be able to do 1 in half a second. So that confirms that, in fact, the period is half a second. So I'll put a check by it. Does that make sense to everyone? Okay. So now that I had that, I'm going to realize that basically we have a scenario where there's a mass on a ball, a mass on a rope. Therefore, we have a tension T. And let's imagine the thing is actually coming out of the page at a velocity V that we don't necessarily know yet. And the free body diagram for that, for instance, is, I'm going to assume the circle goes like this, okay? So that the positive x direction is in fact the direction of the acceleration that it has to have. Because remember, we figured out by taking those derivatives and all that stuff of that vector field, we figured out that the actual acceleration had to point towards the center of the circle and was in the same plane as the circle. Okay. So for this scenario, I'm going to put the ball right here at the origin. And what I imagine on that is, in some sense, it has a normal force that's going to be able to kick up on it a little bit. In principle, it could be like a hole in a table, and you get the thing spinning, and the little string comes up, goes through the hole, and like this, so the thing starts rotating or spinning around on top of the table. Or you could just hold it overhead. When I put a normal force on there, I'm pretending that it's on a tabletop. Okay, but I'm not going to do anything with it because I'm ignoring air resistance and friction and all that stuff. But in principle, it would also have a force mg, and it would have a normal force Fn, but it would also have a tension T pointing this way. And that's the key part that I need. So really all I need is the summation of the forces in the y direction equals mass times acceleration in the y direction. But this is a little different this time. I'm looking at a snapshot, instant in time, of the ball being on the far left-hand side of the circle. And in that case, I have to know that the acceleration, even though it doesn't look like it's necessarily accelerating, it has to have an acceleration, because the next frame it's going to go to a forward a little bit and towards the or right a little bit, because it's going to maintain a circular orbit. So the only force acting on it in principle is the tension T, which I forgot to label. Okay, so that's the tension T, and that's going to be equal to the mass times the acceleration. And what I'm going to say is the acceleration is omega squared r, because I can see an easier way for me to get omega from the information I've been told than I can see an easy way to get the velocity. Okay, so evidently the tension is going to have to be m times omega squared r. So now we can go ahead and calculate that. T is equal to m times omega squared r. That's equal to 0.150 kilograms. Now, omega is supposed to be 2 pi times the frequency, or it can be 2 pi over the period. I'm going to go ahead and use the frequency because that's the number they gave us. So I'm going to say 2 times pi times 2.00 CPS, which again is just another word for cycles per second, for hertz, in other words. So that's my omega, so I'll square that, and then my r is 0.600 meters. So when I do this math, I am going to get 0.150 times 2 squared times pi, 3.14159 squared. Notice I'm just manually squaring each part because I didn't want to put parentheses in my calculator. So I'm just squaring each part. So that's 2 squared pi squared. Now I'm going to say times the frequency, which is 2, and I'm going to square that as well. And then I multiply all that times 0.600. All of this has 3 sig figs, so my answer comes out to be 14.212. And if you look at this, you'll notice that the kilogram multiplied by the hertz squared is kilograms per second squared times m. That's kilogram meters per second squared, which is in fact the Newton. So that's what I actually get for the centripetal, for the centripetal force required. Any questions on that? I did write extra sig figs, so I underlined them. Oops, I don't know why I did that. So centripetal force. Any questions on that, anyone?
Question. What you squared was the angular velocity, right? 2 pi times 2 cycles per second.
Yeah, the 2 pi times f is the formula for angular velocity. So I'm using that version right there. and this is it.
That's what you squared. Okay.
Okay. Now, I'm not sure you students would have thought about that because it's probably been a little while since we did rotational motion and that sort of thing. Actually, no, I forgot. You're 241. I was thinking for a second, you're 242. So you haven't even covered any of this stuff yet. So you might not have thought about using omega. That being said, I'm going to show you an alternative way that hopefully makes a little more sense. So one of the two ways you should be able to make sense of, and then be able to do it from here on out. So here's the alternatively way of solving it. So this is the alternative way. I called it alternatively. Okay. So in this case, what we know is the object's actually going around in a circle, right? And in fact, we're told that it makes 2 revolutions in 1 second, right? So we can use this idea right here that the velocity is distance divided by time. So here's another way of looking at this. We can say AC is equal to V squared over R, and we can say V is equal to distance divided by time. Again, that's the average velocity, but we're talking about a constant velocity, so we can just use it anyways. So what I'm going to say is V is equal to 2 times the circumference divided by 1.00 seconds. Does everybody understand why I said 2 times the circumference divided by 1 second? Right? It says 2 revolutions per second, and it gave us 2.00, which means that the time unit and the distance unit both had to be sufficient to justify 3 sig figs, so I can assume the time's 1.00 seconds. So what I'm going to do is I'm going to calculate the velocity, and the velocity is going to be 2 times, the formula for circumference is 2 times pi times the radius, which is 0.600 meters. And now I'm going to change that parenthesis to a square bracket. So that's my distance, and all this is divided by 1.00 seconds. So that's going to give me my velocity. So I'm going to say 2 times 3.14159 times 0.6. And then I'm going to divide all that by 1. Everything has 3 sig figs, and I get a velocity of 7.5398. Again, carrying 2 extra sig figs because I'm obsessive compulsive. Okay. Now I can go back to the exact same F equals MA statement, that T is equal to MV squared over R. So now I can say 0.150 kilograms. But this time, instead of omega squared R, I'm going to use V squared over R. So I'm going to say 7.5398 meters per second squared. All that's going to be divided by 0.600 meters. Luckily, you see there's no real adding or subtracting in here. So the sig figs are just, however many went in is how many comes out. So that works out really nicely. So I'm going to take and square the 7.5398, and we'll multiply that by 0.150, and then I'm going to divide that by 0.6, and that gives me 14.212. So 14.212 newtons. So not only did I get the exact same answer, I got the exact same answer even out in the non-significant digit area, because the 1 and the 2 were not significant, but lo and behold, that was also the 2 insignificant digits in the previous way. So any questions on that? Okay. So let's look now at another type of typical problem. In this case, what I'm going to do is I would like to compute the minimum speed at which an object can be rotated or revolved vertically. So this is one of those scenarios that you might remember being on the beach doing as a kid, where you take a bucket of sand or water or something like that, and if you spin it at a fast enough speed, it can get upside down, and the bucket will not empty water onto you. So we're going to solve that kind of problem. So this will be another example. I'll call this example 2. Okay, so with this one in mind, I'm going to imagine the same ball that we just had, the 0.150. I'm actually going to put it on a different string this time. Let's say, what minimum, whoa, what minimum speed is needed to revolve a 0.150 kilogram ball in a vertical circle of radius 1.10 meters. Okay, so that's the real problem we're shooting for, and that's going to be part A. And then part B, what will be, oops, actually probably easier to just go back. Okay, what will be the tension at the bottom if the ball is revolved at 2 times v min? Okay, so that's the other part of the problem. So what we're going to use is the summation of the forces is equal to mass times acceleration. We're also going to use the fact that the centripetal acceleration is v squared over r, or maybe omega squared r. Generally, I just use v squared over r. And we're also going to make use of the fact that weight is equal to mg, because we're going to find that the weight is an issue here. So what I'm first going to do is draw the circle. And that's a horrible circle. Now I'm going to let the program make me a better circle. Yeah, that's a perfect circle. Look how good I did. That's amazing. So now what I'm going to do is I am going to imagine the ball right here at the top, and I'm going to imagine, oops, I'm going to imagine the ball right here at the top, and then I'm going to imagine it here at the bottom. I can imagine it over here, and I can imagine it over here as well. The top and the bottom are really the key things here, because if you look at it, when you do a free body diagram for the top, okay, I'm going to draw a coordinate system, and I am going to choose vertically downward as the positive y direction for this particular ball at the top. Okay, so I should also write top here. Okay, now acting on this is in fact a positive force, a force that acts in the positive y direction. So I'm going to make it green, like green for go in a stoplight. Okay, and that force happens to be just m times g. Now, in addition to that, there's another force acting downward. Oops, I'll go ahead and use green for that as well, because it's also in the positive direction. And this force is the tension T. Okay. Ropes can't force anything forward. So the tension always has to be literally the opposite of, or sort of fighting the stretching of the string. That's the way you can think of it as the direction of tension. It's fighting the stretching of the string. So the string, which you might imagine would be right here, that is actually vertical when it's at the top. And of course, to try to stretch it, you'd have to pull it vertically upward. So the tension is going to be vertically downward. You couldn't actually use a string to push upward, in fact, because that's not the way strings work. 2x4s and beams and stuff like that do, but you'd have to, like soak the rope in water and freeze it to make it stiff enough to force it. So we only can have the tension there. But the big thing to recognize is at that top, the actual ball has to accelerate. So we're actually going to have an acceleration. And based on the derivation we did last time, that acceleration has to be downward because that's towards the center of the circle in the same plane as the circle. So I'm going to go ahead and write the summation of my forces in the y direction because that's the only direction that really matters here. So the summation of forces in the y direction equals mass times acceleration in the y direction. But unlike a lot of the times when we work the summation of forces in the y direction, in this case, the y actually has to accelerate. Okay. So what I'm going to do is I'm going to say T plus mg is equal to mv squared over r, and that v squared over r is positive, so that's why I have it written that way instead of with a negative, because it's pointing in the positive y direction, which is the direction it has to go. Now, this is where you can decide what we mean by the minimum speed. So if you actually try to go any speed less than the minimum speed, then what's going to happen is if it was a bucket you were swinging over your head full of water, the water would fall out if you went lower than that speed. Okay. But what is the hallmark of that speed? The hallmark of that speed is when the tension goes to zero, because what's going on is the tension is going to supply whatever force mg is insufficient of supplying. So if mg is enough to supply mv squared over r, then that's sort of the minimum speed at which you can go. If you went slower than that, then the mv squared over r would actually tend to cause the object to fall at the top, as opposed to just staying in its circular arc. Okay, so I'm going to say let t go to 0 to find v min. Okay, so when I do that, that gives me mg is equal to mv squared over r. So we get v is equal to the square root of g times r. So v min, and I should call it that there as well. So v min is equal to the square root of 9.80 meters per second every second, which can be written as meters per second squared, times 1.10 meters. Obviously, both of those numbers have 3 sig figs. I'm going to say square root 9.8 times 1.1, and that gives me, whoa, Nelly. It didn't give me a actual decimal. It gave me some other stuff. So this is going to be 3.2833 meters per second. And notice that when you take g, which is in meters per second, and multiply it by r, which is in meters, you get meters squared per second squared. And therefore, when you take the square root of that, you get meters per second, which is exactly what we expect. So we've now found the minimum velocity. You might be thinking to yourself, well, how do we know that's the minimum velocity? What about the bottom? Well, if we look at the bottom, that's what I'm going to do now. If we look at the bottom, let's see what happens. Okay. This time I'll choose up as the positive y direction, and that's just because up is the direction of the acceleration that we need. M is the mass. So just like I had here a mass M, here I'm going to have a mass M as well. In this case, I'm going to have gravity pulling downward, which is actually a negative direction, and I meant to draw that in a different color, so I'm going to draw that in red. So that's M times G acting this way. And then the tension is actually acting in the positive direction, and that's T right there. Now, it does have to accelerate upward. So basically, the tension has got to, well, let me write out the equation, and then it'll probably be obvious to you what the tension has to do. So I'm going to write out the summation of forces in the y direction is equal to mass times acceleration in the y direction. This gives you T minus mg is equal to m v squared over r. Again, notice since I chose up as the positive direction, then mv squared over r has to be up as well. So it's in the positive direction. So I've got it exactly like I want it there. And what you see is basically that the tension has got to be m times g plus v squared over r. That's a big deal. Okay. That means that not only does the tension in the rope have to provide v squared over r times m for the force required to keep it in a circle, but it's also got to sustain the weight. Okay. If you try to consider that, basically you can see that the tension is definitely, there's no way the tension can be zero. Okay, so that's one way of thinking about it, is the tension can't be zero. Another way of thinking about it is if I put the actual velocity in that I found for V min, I don't suffer any problems with that. So that's just another indicator. If you thought about what's going on at the right-hand side, that's a little different too. You could say, for instance, that gravitational force is downward, and then you'd also say, well, wait a second, the tension is to the left, right? So you see in this case, the mg has no ability whatsoever to provide centripetal acceleration. So the T has to do it all. But unlike the bottom, the T only has to provide mv squared over r. It doesn't have to provide mv squared over r plus mg. The same thing happens over here. That's mg this way, and that's T this way. So we get the exact scenario there. And everything in between is just slightly, a little bit different because, for instance, when we're right here, for instance, yes, mg acts downward and tension acts in a totally unrelated to the coordinate axes way. It points towards the center like that. So you have a component of tension or a component of weight that's parallel to the tension. So you can see there is a little help. And in fact, what this is telling you is that the weight will actually tend to speed the ball up as it passes the top and starts to go to the left. Not only that, if you look at it to the right of the top, so if you put it right here, you'd see that the tension points this way, and mg, of course, still points straight down. Now, in this case, what you see is the tension, or excuse me, I wrote tension there. That's why I said tension, I think. Oh no, that's a different tension. No wonder. That's mg there. What you see here is the velocity, which would actually be going this way, for instance. That velocity is being slowed down by mg, by the weight. So what you sort of see is if you're at the top, you can have that minimum velocity, but as soon as you leave the top, it's going to speed up, speed up, speed up, speed up until it gets to the very bottom, at which time it'll have its maximum speed. And then as soon as it gets past the bottom, the mg is going to start to slow it down, slow it down, slow it down, and it'll continue to slow down until it gets back up to the top. Okay. That's part A. We're done with that. So now we're going to do part B. And we've sort of already done part B just by drawing the F equals ma and the free body diagram at the bottom. So that's what we're going to do now. See free body diagram and Newton's second to the left. Okay. So what we get is tension is equal to M times G plus V squared over R. And what we have here is V is going to be 2 times V min. Well, that means this is going to be 6.5666 meters per second. That's going to be the velocity. So now I can compute the tension T, which is equal to 0.150 kilograms times 9.80 meters per second every second plus 6.5666, two extra sig figs there, meters per second squared over 1.10 meter, like that. And when I do that, this number right here inside the bracket is going to become 49.000. So that's just something I happen to remember from doing it earlier today. So I'm going to take and I'm going to take that 6.5666 and square it. And then I'm going to divide it by 1.10. And that gives me 39.2. So it's good to 1 sig fig. And then when I add that to 9.8, that gives me the 49 point, the 49.0, and it's actually good to 3 sig figs. So now we have 3 sig figs again. Now I can multiply that by 0.150, or excuse me, 0.110. And that gives me 53.9 newtons. So that's what the actual tension is when we do twice the minimum speed and try to figure out what the tension is at the bottom. The tension is obviously always going to be a minimum at the top and is always going to be a maximum at the bottom. Okay. The big thing to notice from both of these is that, yes, you can actually use an accelerating reference frame as a sort of snapshot in time, that F equals ma has to be applied at least at that split second in time, even with the fact that the acceleration is actually moving. So it's okay to do it the way we did it. That's the main thing. And your book talks about that. And I think I even highlighted where it's making the argument. So that's supposed to be a highlight that you guys can see. I'm not sure now because I'm not seeing it. That's aggravating. Okay. Anybody have any questions on any of that? All right, your book does do a conical pendulum, which I think is really great. I don't think it's enough bang for the buck in terms of using time to teach you stuff. So I would rather let you figure that one out on your own. It's not that big a deal. If you do have problems, though, by all means ask. Remember, I am moving the test back, but it's not adding more material. So this chapter 5 stuff is not going to be on there. So I'm going to go ahead and skip the example 513. And I'm going to go to another problem altogether. And this one's an interesting problem that maybe you're just not, you've never thought about. So let's do that. What I'm going to do is I'm going to draw the Earth. So that's the Earth. And the Earth, of course, I hate when it does that. So there's the Earth. We know, for instance, is rotating that way. Okay. And I'm not even thinking about the Earth moving in an orbit around the sun. I'm just thinking about the Earth rotating about its axis. Okay. Now, what we can imagine is I'm going to put a scale on the equator, and then I'm going to put my nary little butt up there. See how nary I am? And what I want to do is find out what's my apparent weight. And just to make it interesting, I'm also going to do the same thing for the North Pole. I'm going to put a scale there again. And I'll say the person has a mass M, which when need be, I'll actually make that 100.0 kilograms so that it has 3 sig figs. And the person is going to have a mass M here as well. Okay. What I want to know is F apparent. I still don't know whether apparent has 2 P's or not. I've been writing the 2 P's really close to each other so I can fake it. But that's not necessarily the best way. So I'm going to say the apparent weight is question mark. Okay. So I think everybody understands what we're trying to say here. So again, this is just like the other problem where I'm actually dealing with a accelerating reference frame, at least in the equator case. Okay. Now, what we'll notice is when the Earth is rotating, then us at the North Pole just sits there and go like this. In fact, if you were lucky enough to get to go to the North Pole, which is a whole different thing all by itself, and two, if you were further lucky enough that the sky was actually clear for a whole evening, then you'd be treated to the really interesting thing that you never get to see, and that is the stars neither rising nor setting. In fact, the stars would just go from left to right in a circle all around you like this. I mean, that's kind of cool, right? You don't get to see stars do that every day. So because of that, there is no velocity. There is no velocity and no need for an additional acceleration towards the center of the circle because gravity is just going to hold it there. So I'll draw a free body diagram for this case like this. I'm going to treat this as my y-axis, and I'm going to say this is my person of mass M. That person has acting on them in the positive direction a force F sub S. Now, if this was a table, I'd be normally calling it the normal force, but I'm wanting to point that out to you now because in reality, that's, the scale force is what the scale is going to read, and it is essentially a normal force. In other words, if the person was standing on a table instead of a scale, then the table would have to supply exactly the same force as a normal force as the scale does as F scale. Now, in addition to that, we have a negative force, a force acting in the negative direction, which is just M times G. Okay. But in this situation, there's no acceleration. The object's going to stay the same distance from the center of the Earth the whole time. The object will be rotating about an axis through the center of them. But again, that's no linear motion of any sort. So what we're going to get in this case is the summation of the forces in the y direction is equal to mass times acceleration in the y direction. And the acceleration in the y direction is 0, like the inclined plane problems we've been solving. So what that gives us is that Fs minus mg is equal to 0, and we find that the scale reads the actual weight of the person. Now, actual is a word that I do know how to spell, so I'm going to write that boldly and proudly. Feel free to pick on me later about my lack of ability to read. Evidently, to spell. Evidently, the computer has not been good to me because I used to be a phenomenal speller. I'm not so much anymore. Now, here's the interesting thing on the equator case. So if I'm talking about the equator, then I'll draw my free body diagram right here. And in this case, I'm going to draw my x-axis pointing to the left, and I'm going to draw my y-axis pointing up, even though I don't really need the y-axis. I'm still going to put my person of mass m on the situation in the setup. And in this case, the force of gravity, the weight, for instance, is actually pointing in the positive x direction, and the force of the scale is actually pointing in the negative x direction. So this is F scale. And now if I change colors, this right here is mg. Okay. So now I can take the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, the object has to, the actual person has to be accelerating towards the center of the circle. If he didn't, then he'd get right there on that spot of the Earth and just shoot straight backwards perpendicular to the page. Right? That's what inertia would make him do, because his tangential velocity at the right-hand side of the Earth's sphere is actually into the page. So he would just take off straight through the page and go on forever at that fixed velocity until, you know, some gravitational force pulled him or something. So now what we have from this is Fs minus mg is equal to, notice the acceleration has to be towards the center of the circle, which is to the left, and that's the direction I called positive. So that's m times v squared over r. Now, what I will tell you is that the radius of the Earth, which is normally written as a r with a circle with a plus in it like that, is 6.378 times 10 to the 6 meters. And I will tell you that I don't know the velocity of the Earth off the top of my head, not the velocity of the as a particular spot on the equator. I don't know that velocity off the top of my head, but we're going to calculate it. Okay. And what I know is the Earth makes a complete 360-degree rotation in 23 hours, 56 minutes. Yes, I meant that. Okay. It turns out that an actual 360-degree rotation is not a day. A 360.986-degree rotation is a day. That's what takes 24 hours. But this takes 23 hours, 56 minutes. But I'm going to ignore the 3 minutes because 3 minutes out of 24 hours is a pretty small change. So we'll just ignore that. So we got to have v squared, we got to have r, all that good stuff. So let me calculate v. V, like we used before, is equal to distance traveled divided by time taken. This is going to be a constant one. So just like before, the average is the velocity. So the distance is going to be the circumference of the Earth, which is 2 times pi times 6.378 times 10 to the 6 meters. And I'm just a nerd that happens to know that. And now I'm going to say the time is 24 hours. And I might want to make sure everybody realizes that's in the numerator by putting it over 1 and then multiplying that by 3,600 seconds over 1 hour. And you can see there that the hour cancels out with the hour, and that gives me everything I need. So now that I have that, I can go ahead and do the calculation, and then we'll have an actual estimate of how fast the equator of the Earth is moving. Okay, again, this is just the velocity due to the rotation of the Earth. This does not include the revolution of the Earth. Okay, so our stuff just turned out. So 2 times 3.14159 times 6.378 times 10 to the 6. Now I'm going to divide all that by, and here's where you use parentheses just in case y'all are old and rusty. because it's been so long since you did basic algebra, use your parentheses, because if you do 24 times 3600 in the bottom without parentheses, then it'll definitely divide by 24, but the 3600 is going to multiply by because it knows the order of operations better than we do. So now that I compute that, I get 463.82 meters per second. And that's supposed to be the velocity due to the rotation of the Earth. Remember, that's 463 meters per second. So you're looking at like 2.5 times faster than that in miles per hour. So we're definitely looking more like 1,500 miles per hour. So that's quite a bit, or maybe not 50, maybe 1,200 or something. Okay. So now that I have that, I can finally say that the scale is going to read a force of m. Notice both of them have an m, so I'm going to write it as m times g plus v squared over r, which I'm going to write as 0.150 kilograms times 9.80 meters per second every second plus 463.82 meters per second quantity squared over 6.378 times 10 to the 6 meters. And then close the square brackets. So first off, I'm going to compute the v squared over r term. So I'm leaving room for that. That's why I'm writing all these numbers, even though I already know them. So I'm taking that 463.82 and I'm squaring it. And then I'm going to divide that by 6.378 times 10 to the 6. And that gives me 0.0333730 meters per second squared. Again, keeping up my tendency to carry 2 sig figs extra, or 2 extra digits. Okay. So now I just have to add that to 9.8. You can see it's really not that big of effect because it's only 3 in the second decimal place, but still it's an effect. So now the acceleration in here is 9.83. Ooh. Okay. So now I multiply that times 0.150, and that gives me ultimately what is stupid me. Where did I get the 0.150? Oh, I remember that from the previous one. Stupid head. The mass, remember, I wrote right here, was supposed to be 100 kilograms. I guess I just remembered the 0.150 from the ball earlier. So let me put that back in correctly. Okay, so that's the, oops. Yeah, that's good enough there. I'm also going to erase it here so it don't look confusing how all of a sudden 0.150 became 100. Okay, that was terrible. So what I'm going to do is take that 9.83 and I'm going to multiply it by just the 100. So this is going to be 983.37 newtons. So my apparent weight at the equator is 983, roughly 983 newtons, whereas Fs equals mg on the pole, on the North Pole, is just 100.0 kilograms times 9.80 meters per second every second, which is 980.00 newtons. So in this case, you can see that really it's only about 3.37 newtons. Hey, that's supposed to be minus. No. Yeah, why did that come up? Hold on a second. V squared over R, that's right. MG's that way. FS is this way. Where was my equation? FS minus MG. Oh, that's why. Okay. Notice everybody, I don't know how I did this. It should actually come up to less weight, not more weight. And I didn't realize it until I did that. But notice, let's look right here. Do you see anything wrong with that compared to this diagram?
It should be plus.
Yeah, instead of FS minus MG, it's supposed to be MG minus FS. So what I'm going to do to make it clear what's going on is I'm going to say, put a red mark through this and then write MG minus FS. And when I have that, I'll say, I'm going to pull it over here and say MG minus FS is equal to positive MV squared over R. That means MG is equal to MV squared over R plus FS, which means you can now say that FS is actually equal to M times G minus V squared over R. Whoa, I wrote an 8 there. I don't even know what that was. Okay, so the long and short of that is this quantity should be a negative. So instead of 9.83, we get 9.80 minus 0.33730 gives me, whoa, 9.80 minus 0.033730 gives me 9.76. So 9.7663 is what that acceleration is. And then this line is going to be 9.7663 times 100, which is clearly 976.63 newtons. Okay. So that's the weights we should compare. And what we see is, yes, you do lose a little bit of weight by going to the equator, at least some of the apparent weight, but notice it's really small. It's basically 0.3 or 0.03. Well, I guess we could go ahead and say it's a little bit bigger than 0.03. Basically, we're doing 980 versus 976, which I'd round to 977. So it's like 3 newtons. And remember, a newton's about a quarter pound. So we're not even talking a whole pound difference, but there is a difference. That's the key thing. So sorry about dropping that negative. I wish I would have called it earlier, but there we are. I'm going to also, just to make sure we're correct, this is going to be have to be negative as well. So I just put that there. Anybody have any questions on that? Sorry about botching that up. Any questions? All right, so now I don't have much time, but I have to do some curve banking stuff. So let's start off with the idea of a flat curve and see how fast you can go around the curve for a given friction coefficient. So let's imagine, for instance, that we have a level ground, perfectly horizontal. A car is driving on it, like so. And we're going to assume the car is trying to make a turn to its left or right. Okay. Let's say the radius of the turn is 50.0 meters and the coefficient of static friction is 0.60. And that's going to be for part A. And then for part B, the coefficient of static friction is going to be 0.25, which is more like ice. And the 0.60 is more like dry pavement. And let's say the car has a mass of 1,000.0 kilograms. Okay. What we want to know is, in this case, I think I'm going to choose, I'm going to choose, instead of trying to find out what the max velocity is, I'm going to actually ask, will it actually spin out or not at the velocity I'm given? So I'm going to give you a velocity when it's not on a banked curve, when it's on a flat curve, and I'm going to say the velocity is 18 meters per second. So V equals 18.0 meters per second. And question A is, will it make the turn? And then question B will be ditto. Now, I use that phrase today, so just in case any of you are having similar problems, I had two people whose native language was not English, so they didn't know what ditto mean. That just means repeat everything I just said. Okay. I also went further and said, by the way, if you really meet a woman that you really, really are digging and you really, it's gone a long way and you're feeling really great about her, and she ever says she loves you, just say ditto back. They love that. So anyways, let's go ahead with this. In order to do this, I'm going to draw a free body diagram. And what I'm going to imagine is this is the positive x direction. Specifically, I'm doing that because I want the acceleration that we have to have, the centripetal acceleration, to be in the positive direction, so I don't have to have any negative crap. Okay. That's going to be my y-axis. What we have acting on the car, of course, is going to be a upward force. That's the normal force, like that. And then we're going to have a downward force that is mg. And also, since we're trying to turn to the left, a force must be able to push back on us when we try to go to the left. So we're actually going to need a force to push, a force to push to the right on this diagram. And that force is going to be the friction force. And it's specifically the static friction force. So if I choose to write my solution, let's say in purple, what I can do is say the summation of the forces in the y direction equals mass times acceleration in the y direction. We're not imagining the car jumping off the pavement or anything. It's going to be staying relatively still vertically. So the acceleration in the y direction should be 0. And from that, we get Fn minus mg is equal to 0, which gives us equation 1, Fn is equal to mg. Okay. Now the summation forces in the x direction equals mass times acceleration in the x direction. This time we actually do have an x direction acceleration. but we only have one force acting. And what we're going to do is assume that the force Fs, well, I did it a different way in class today. I think I'm going to go ahead and set up the equation and then do it a different way than what I did in class. So the only force we have acting to the right is Fs, and Fs is equal to mv squared over r. So, by the way, Fs max is mu static times F normal, which would be 0.600 times 1,000 kilograms times 9.80 meters per second, which gives me 9.8 times 1,000 times 0.6. The 0.6 is why I'm doing this, is 5,880 newtons, and only 3 of those digits are significant. So I'll call it 5880 and underline the 0. So that's the max the static friction force can be. So now I'm going to take what's equation 2 and compute it. So Fs equals 1,000.0 kilograms times the velocity, which is 18.0 meters per second squared. And then I'm going to divide all that by 50.0 meters. So I'm going to do 1,000 times 18 squared divided by 50. And that's going to give me 6,480 newtons. Again, I only get 3 sig figs. Notice that is actually bigger than F static max. So that means it's not going to make it. Okay. Now, if that didn't make it, the ice one didn't make it either. I think I'm sort of using the numbers that the book had used, and I think it used like 15 meters per second or something. And at 15 meters per second, it works okay. But at 15 meters per second, it does not work okay in the snow case. So for part B, I'd say no as well, because mv square, or in this case, F static max is equal to 0.25 times 1,000 kilograms times 9.80 meters per second per second. That gives me 2,450. So again, Fs max is less than mv squared over r, implies no. Okay. Now we only got like a minute and a half left. Let me quickly show you how to do this. If we had an inclined plane like this at an angle theta, okay, the car would be sitting up here and everything. But the most important thing is the free body diagram. So what I'm going to do is draw a free body diagram like this. Ooh, not like that. I'm going to draw my X and Y coordinate system like this. I will tell you that inclined planes are almost always a time where you should use a tilted coordinate system. But when you're solving for a curve like this is the only time you definitely do not use it. Okay. So what we're going to imagine is that this angle right here, theta, is in fact the same theta as down there, but that's the angle between the y-axis and the normal force. Okay, so that's the y-axis and the normal force. The gravitational force actually points in the downward direction, so that's mg right there. And in principle, that's all the forces you're actually allowed. Okay. So we have to actually break up the normal force into a component in the x direction, which is the direction of the centripetal acceleration, and then in the y direction, like that. And we can actually say this angle up here is going to be theta now. It would be the same thing if I drew the green vectors over here. You'd still get the same result. But I'm going to take the summation forces in the y direction equals mass times acceleration in y direction. The y direction should have zero acceleration. From that, I'm going to get Fn cosine theta minus mg is equal to zero. So from that, and this is a weird version, from this, the normal force is mg over cosine theta. So that's a whole new thing that you're not used to. I just want to show you that. Now I'm going to do the summation forces in the x direction equals mass times acceleration in the x direction. Now in the x direction, I have to actually have an acceleration that way. So what I'm going to do is say Fn times sine theta is equal to mv squared over r. And now you can put in that Fn is equal to mg over cosine theta. That's going to give me mg over cosine theta times sine theta is equal to mv squared over r. The m's cancel out, and the sine theta over cosine theta becomes tangent theta. So now I've got g tangent theta is equal to v squared over r. I can say theta equals the tangent inverse of v squared over gr, and that's your answer. All right, sorry to go through that so quickly. I just didn't want to miss another opportunity. You can look for more explanations on my YouTube channel, or Khan Academy or stuff like that. But you guys are free to go. I hope y'all are happy that I did move the test back. I hope no one's upset about it. I hope you also read your email that I sent about that. Let me know if you really were bummed out or got messed up by me rescheduling it. If you did, I can probably find a way to test you this week as opposed to next week. So just let me know if that it really is a problem. And like I said, I've already worked out a deal for those people who were I call them diligent, but I'm just saying they were, sort of go-getters. They went ahead and took the test early. So anyways, I told them what they had to do if they needed to, if they took the test early. So have a good one, everybody. Have a nice weekend. And we are planning on having the test on Tuesday, or excuse me, on Monday of next week, but I'm perfectly cool with doing it Tuesday or Wednesday if you try. So please reply to that email. Have a good one.
I do have a question. Could you move the practice test back to the
Yeah, that should definitely happen. And I think I might have already done that.
Oh, okay. It's just
Uh,
earlier.
yes, 241 N02B. I moved it now to be due October 14th. But if we end up pushing the test to Wednesday instead of Monday, which I'm waiting on you guys' response for that, then I'll move it back to that day. What day is 14th? Is the 14th Monday, like I'm remembering?
14th is
Yeah, it's Monday.
Monday.
That's cool. So yeah, if enough of you say that y'all want it on Wednesday, I'll probably move it to the 16th instead of the 14th, and then I'll change the practice test date too. Anybody else have any questions? Is that helpful, Andrew, or do you have something else?
No, I'm good on questions.
Okay. Feel free. We're short on time for catching me on email and stuff like that. So if y'all have any last minute questions regarding test stuff, then send me a text. It's okay. I might not respond to you immediately, but I will respond to you when I get a chance. And that'll probably come a lot quicker than you sending me an email. So feel free to do that. Even if it's 2 o'clock in the morning, I've got my phone turned off, so it's not going to bother me.
Professor,
Yes, sir.
sorry, I was actually taking the test. That's why I came in late, and I saw your email like after the fact. Is that the dates, is that for you to proctor it or just for us to schedule it again with like the testing center?
Yeah, I'm going to give you the whole next week. Oh God, that's what I was saying. No, I'm sorry. You guys have the whole next week. I don't know why I said Monday or Tuesday. In fact, let me change that right now on the practice test. I'm going to give you all the way till Sunday of next
So-
week. So not this coming Sunday, but thereafter. So I'm making it until the 20th of October.
Okay, so we have until then to take the 1 through 4, chapter 1 through 4 tests.
Yes. Yeah. So
Okay.
sorry about that, everybody, about saying it was Monday. I was thinking of the normal stuff here instead of the fact that y'all are taking it to the testing center.
And we can still do that through a testing center?
Yeah, you just as long as you can find another time to do it. I only got a couple of you that actually took it, so I don't think they're going to complain too much about you taking it a second time. But I'll go ahead and submit the other one. And like I said, you get all next week to take it, and up until Sunday of next week, which is the 20th.
Okay, cool. And the next thing that practice test, I think I had the same issue where like only 4 problems were populating out of the 10.
Okay, I thought I fixed that. Let me double check and see. Is this still messing up, Jennifer? I think you were on it most recently.
It was messing up today earlier. I haven't seen it since earlier today.
Okay, let's look. I'm going to pull it up right now and see what's going on.
The rest of the questions are spacers.
Yeah, this should have 10 questions. It should have 4 concept questions at 2.5 points each and 6 questions at 15 points each.
Yeah, I get the first 4 conceptual, but after that it just goes straight to the formula sheet and then it's like the submit option.
Is the test you're taking called PT_03, chapter 1 to 4?
Yeah.
Okay, try submitting it. If it opens up and only has 4 problems, just try hitting submit even with nothing answered, and then go back in, see if it does it. Another thing you might want to try is emptying your cache.
Okay.
Give that a try and let me know if it's still doing it, because from this side it looks like it's working now, but it was broke before, so
Yeah.
hopefully something weird happened, but that should take care of it. If not, I'll make a whole nother test. And again, communicate with me through text instead of email, so you'll get it quicker and I can respond quicker.
Okay, cool.
It is populating now on my end.
It is
Awesome.
good deal.
Okay,
Got
cool.
10 questions now.
That's cool. Appreciate it.
And
Thanks,
sorry,
guys.
is there class next Monday? I know it's a holiday. I can't remember if.
Yeah, we don't have any more days off until Thanksgiving.
Okay.
Except for, we do have like November 5th off because that's a election day. But other than that,
Okay.
we
But okay, Monday and Wednesday are just normal class days.
far as I know, yeah, I don't have anything listed as that being a
Okay.
special day, or I'm looking at my calendar. I didn't mark anything like that.
Gotcha. You're not proctoring the tests or anything, right?
No, but I can if anybody needs it and they can't fit into the times that the testing center has. There's ways I can
Gotcha.
proctor.
Okay. Yeah, I should be able to fit it in at the testing center. So sounds
All right.
good. All right.
Appreciate it, Alec.
Yeah, no problem. Thank you.
Have a good one.
You too.
Thank you.
Mark or Jennifer, do you have any questions? You're welcome, Jennifer.
No, that covered everything, I believe.
Cool. Well, I hope that was good news that you got today. It looks like Mark is raising his hand. How can I help you, Mark? And you can type it in the chat if you need.
No. So I got a
Oh, it's Mark.
question about the practice test 16 to 18. It's still not open, so I can't take it yet. And I got a question for one of the problems in my 16 to 17 test.
Okay. I tell you what, let me set this to where I can, more than one person can share. Well, that's not it.
Oh, and also I just checked the Gmail. So is our test being delayed?
Yes.
Okay. Yeah, I
Yeah.
just heard you talking about like a test being delayed during the Zoom class, and I was wondering if that's gonna apply to our class as well.
Yeah, I just sent out an email about that just because I felt bad. Your class has been so diligent and working hard with me and stuff like that. I was like, well, they might could use the extra time, so I decided to do it. You're the guys I was actually talking about. Would you prefer to have it on Tuesday or Thursday? So feel free, definitely email me, let me know whether Tuesday or Thursday's preferred, and I'll gladly move it to Thursday as opposed to Tuesday, but hopefully that should take care of it.
Okay, okay.
I'm going to
Yeah.
try to pull up that practice test now for
Mhm.
your class and see if it's working.
Yes, it still say it's logged on October 9 at 9:30 a.m. for me.
Okay. I'm putting it open as we speak. So this was a practice test. Ah, there you go. Oh yeah, stupid me. I did do that, but I did it in the wrong class. Crap.
Oops.
So yeah, that's what happened.
Okay.
I'm
And
gonna now move it to, I'm gonna move that to the 15th. And if you guys decide that you want to take it Thursday instead of Tuesday, then I'll move it to the 17th.
okay, okay. And I got one final question for the online test that I took for chapter 16, 17.
Okay.
Can
Let's
I
go
share
ahead
my
and share
screen?
it. And I just removed my stuff that I had on the screen.
Okay. It's this one. I made a guess here, so I have no idea on how to start it.
You talk about the one that's highlighted in blue?
Yes, question 5.
Okay.
Like,
It says a negative, or excuse me, a positive 5 microcoulomb point charge is placed at 0.0 centimeters mark of a meter stick, and a negative 4 microcoulomb point charge is placed at a 50 centimeter mark. At what point on a line through the ends of the meter stick is the electric field equal to 0? Okay. So notice by putting two charges up, you've got three places to inspect. You've got between this side and this side, right? So if we put them between, one's positive and the other's negative. So with the positive here and the negative here, if this is the positive, then it's going to create an electric field pointing that way. And if this is the negative, it's going to point an electric field pointing that way. So there's no way those two that point in the same direction can cancel each other out to give 0. So we know it can't be the middle. If we go over to this side over here,
okay, I
okay,
got you.
and you see me in the picture? Actually, let me go ahead and I'll tell you what, I know the answer now. You got negative 4, positive 5, 0, and 50 centimeters, right? And the negative is at 50 centimeter. Okay.
Yep.
All right, I'm going to put it on a new page and I'm going to go ahead and share real quick.
Okay.
Still not come up yet. Hold on. Might help if I actually do my part. So I'm going to imagine this is our meter stick that we're talking about. I'm going to say this is 50.0 centimeters. And then I'm going to say right here is the negative 4.00
4.14 coulombs.
microcoulombs. Thank you. And actually, I should probably make the x-axis go a little further along so I can make room for whatever I'm doing here. And this is 50 centimeters. And then over here, I'm going to put, well, maybe not there. Let's do it a little closer. Let's say right here, I'm going to say 0.00 centimeters. And at this location, I'm going to put a positive 5.00 microcoulombs. That's right for those numbers, right?
Yes.
Okay. So when I do the electric field, notice I drew them different colors. So since the green charge is positive, that means between it, the electric field would point this way.
Toward the negative charge.
And for the negative charge, it's also going to point that way.
Mhm.
So 0, not possible.
In the middle.
In the middle, right? Now, if I go over here, then in this case, the negative force or the negative charge creates electric field this way, and the positive one creates a negative electric field this way. But notice it's only, 25% larger in charge than the 4 microcoulomb. So, and it's quite a bit farther away in terms of distance. So this side over here is just not likely. If it had any chance, it might be this side because we actually have the 5 microcoulomb is going to cause a larger force than the 4 microcoulomb, but I'm not sure that it can make up the whole 50 centimeter difference. So we'll put that on ice for a second. Now, if we consider over here, the electric field due to the positive charge is this way, and the electric field due to the negative charge is this way as well. In this case, there's absolutely no way it can make up for it at all because I'm way farther away from the force from the negative 4 microcoulomb than I am from the 5. And the only thing that the electric fields can depend on is the charge and the distance. So this is just not possible from a numerical standpoint. So this is not possible because E sub 5 is greater than E sub 4. Okay, so we're going to have to stick with this one over here. The 4, or the electric field due to the blue one, which I'll call E sub 4, is actually going to be, and I'll put a vector symbol over it because it's, well, I don't want to put a vector. Yeah, I'll put a vector symbol over it. Now just remind you that the vectorness of it is covered by it being negative or positive. The negative meaning it points to the left, the positive meaning it points to the right. So the electric field for this one is K times negative 4.00. Actually, that is in the negative direction, so that works out okay, times 10 to the negative 6 coulombs divided by, now in this case, the distance between the negative charge and the point is what I'll call X. And that's got to be squared. Okay. Now the electric field for the 5 one, that is going to be K times positive 5.00 times 10 to the negative 6 coulombs. Only this one's going to be 0.500 meters plus X squared.
Okay.
Okay.
Is it because it's 5 centimeters away from?
50 centimeters away.
Yeah, 50 centimeters away.
Yeah, so when you convert 50 centimeters to meters, it's 0.50. So I've got to make up for the 0.50 plus X being the distance.
So we're using E4 as the base area and E5 as the Q2 area?
It's actually the formula. That's just basically the Coulomb formula. And I'm saying one's negative and the other's positive because they're asking you, can you find a place where the electric field is 0? So what I'm going to do is I'm going to say negative K 4.00 times 10 to the negative 6 over X squared plus 5 or plus K times 5.00 10 to the negative 6 over 0.500 plus X squared is equal to 0. Since it's equal to 0, you can divide through by K. And that gets rid of that K and that K. So you don't even need those. But what you now have is you have a problem where you can put the negative on one side. So that'll be 4.00 times 10 to the negative 6 over X squared. is equal to 5.00 times 10 to the negative 6 over 0.5 plus x quantity squared. Sorry, that plus turned out really bad. I'm not keeping the extra digits for that particular part. Now, not only that, notice the 10 to the negative 6 cancels out on both sides. So we can make it a little simpler on ourselves. So what I'm going to do is cross multiply, and I'm going to get 4 times the 0.5 plus x. When you actually square that, you're going to get 0.25, because half times a half is 50. And I'm actually supposed to have 3 sig figs, so I'll put that like that. Then I got to do 2 times 0.5, which is 1 times x.
Wait,
So
hold
this
up.
is
I got a
plus,
bit
yes?
I got a bit lost when you were dividing by k. So like, why did you get? Hold up. Yeah, it's around like where you divide by k. I got a bit lost. Like
Okay.
I was writing stuff down and then
So
stuff
what I
happened.
did is, you can imagine it this way. Now that I got rid of k, I just have this number with this negative sign and
Yes.
this number and this positive sign, right?
Huh?
So
Oh, I see now.
if I
So
pulled
you,
this over here, it become negative, and then the
yep,
negative
and then
would,
you took the negative and it become positive again.
exactly.
Mhm.
Okay.
And where do you get the 0.25 from?
That's 0.5 times 0.5, because the FOIL, there's a trick to doing a square of a binomial. But basically I'm just doing FOIL, 0.5 plus x times parentheses 0.5 plus x. So I've got to distribute all that. So the first term, you have to square it. Then you have to take 2 times the product of the 2 terms. That's the middle one. So if I take 2 times 0.5 times x, I just get plain x. And now I have to take the square of the last term, which would be plus x squared. So that's what I got from that one. Now on
Okay,
the
so
other
you follow
side,
it.
I'm going to get 5 times x squared. What's that now? What did you say, Mark?
Okay, now I think I get where you got these numbers from. I think I understand.
Okay. Now I can distribute that 4. And when I do that, that's going to be 4 times 0.25, which is just 1 again. So this will be 1.00 plus 4.00x plus 4.00x squared is equal to 5.00x squared. Now I'm putting the sig figs back in. Now I can pull the 5 over to this side, and then I'll have it in quadratic form. What's going to happen though is I'll have negative x squared plus 4.00x plus 1.00 is equal to 0. So x is going to be negative b, which would be negative 4.00, plus or minus the square root of b squared, which is 4.00 squared, minus 4 times a, which would be negative 1, times c, which would be 1. All that divided by 2 times a, which would be 2 times negative 1.
Oh wait, I remember this formula. It's what was that formula
Quadratic,
called again?
the quadratic formula.
Yeah, that's it. Quadratic formula.
Yeah, a x squared plus bx plus c equals 0 implies x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a.
Okay.
So when I square that 4, I get 16.0 with an extra 0 there. And then I get plus 4.00. So that's actually going to give me 20.0 under the square root. And this gives me negative 2.00 in the bottom. So I can say negative 4.00 minus the square root of 20.00 over negative 2.00, or I can take the top signs, which be negative 4.00
0 plus the
plus
square root of 20
Exactly.
-2.
Okay. This one is square root of 20. I'm going to do square root 20. And I'm going to make that a decimal. So that's 4.47. And I'm going to say minus 4. And then divided by -2. And that's equal to -0.2361 meters. But that's a negative, and that doesn't make any sense, of course. Now, if I try the other one, I'm going to say -4 minus the square root of 20. And now I'm going to divide that by -2. That gives me 4.23. 61 meters. So evidently, if you make the distance between the 50 centimeters and the X 4.231 2361, then that should do it. That does not seem like a very nice answer, but that's what it came out to be. Does that make sense how we did that though, Mark?
Yes, I understand now.
Okay.
Well, I'm trying to take a picture, but there you go. But yeah,
And
I get you now.
remember this document is always saved on my Google Doc. So if you ever need any of the documents from classes or whatever, you just look them up by the name. The name of this one, for instance, today was my PHY 241 N02B class, and it was on 10/9/2024. So that's the actual name of the file. So when you're looking for that, all you have to do is do a search for that date.
Okay. Let's see if I remember how to access your document again.
All right, I'm getting a phone call. You mind if I split, bud?
Yeah, okay. Yeah, you've been helpful. Thank you.
All right, have a good one, Mark.
Thank you, Professor. You too.
You're welcome. Hey, baby.